Hello, and welcome to this edition of the CSIAC podcast series. In this episode, we'll be exploring the utilization of Berkeley packet filter, BPF tracing, as a means to monitor high-performance computing sites with minimal performance degradation. Information security practitioners must secure high-performance computing environments for government research contracts. However, the solutions they architect cannot reduce performance by more than a defined percentage. Known as supercomputers, HPC clusters utilize numerous machines to deliver a powerful computing environment. Sizes range from dozens to tens of thousands of nodes. Large clusters share their resources among many users. A current approach to HPC security is to lock down a few login nodes with required security controls and only lightly monitor the isolated compute nodes behind them. These compute nodes are referred to as the soft underbelly of supercomputing. This podcast will discuss Berkeley Packet Filter, BPF, as a general tracing tool for detecting malicious activity on Linux systems, a summary of recent developments in BPF, and an explanation of its usage is provided. We'll also evaluate BPF as a security tool for production HPC clusters, both from a performance perspective and a detection perspective. To validate BPF, a series of low-profile attacks are conducted against 8 compute nodes running a series of benchmarks. Benchmarks without BPF probes are compared to benchmarks with BPF probes to determine the performance loss. The logs of the BPF trace scripts are compared with the attack script logs to determine the attack detection rate. The architecture of an HPC cluster can be very basic to extremely complex. An HPC node provides a multi-compiler and multi-version environment intended to support scientific software from many different disciplines. Researchers initially authenticate to a login node session. Once a researcher is ready to launch their software on the compute nodes, they submit a job to the scheduler. Compute node operating systems are installed using scalable provisioning technologies. Firewalls and network monitors are not usually deployed for compute nodes. Security practitioners must deal with various issues regarding compute nodes. For example, compute nodes can run arbitrary code, they can access centralized research storage, produce highly variable network traffic, they have fewer security controls for performance, and they produce terabytes of network traffic per second. BPF was implemented in 1992. It was 20 to 100 times faster than competing packet filters. BPF has changed greatly in the past decade. The BPF virtual machine was used to filter allowed syscalls instead of network traffic. A patch set was posted that greatly improved the BPF performance, as well as a patch that demonstrated using BPF for tracing filters. BPF was further extended by moving BPF out of the network subsystem into its own directory and implementing a new BPF syscall. This improved BPF implementation is known as Extended BPF or eBPF. The BPF Compiler Collection, BCC, was created to address an issue with the BPF syscall. It greatly simplified the process of writing tracing tools that could leverage BPF. There are more than 100 BCC tools currently available for monitoring system calls, language function calls, network events, file system performance, and database performance, among others. Let's examine some of these tools. The first tool is OpenSnoop. It traces open and open-at syscalls. The tool can detect a user's failed attempts to list the root directory as well as view. Next is the exec-snoop tool. It traces new processes via exec-sys calls. It can detect a user attempting to run nc, download ncat, as well as create and run a suspicious Python script. The TTY Snoop tool displays the output of a TTY as if the administrator is sitting at the same terminal. And finally is the TCP States tool. It can be used for tracing any TCP state changes involving remote ports 22, 80, or 443. BPF Trace is an intuitive tool that's built on BCC and BPF, which offers an AWK-like syntax familiar to many systems administrators and security practitioners. It is now a full-fledged tracing utility that can use a wide variety of sources and trigger many types of actions. The software includes over 30 high-quality scripts that cover dozens of system activities. We'll now examine the performance impact of BPF when monitoring compute nodes under heavy load. While the effectiveness of a security solution is crucial, HPC administrators need assurance that security tools will not unacceptably degrade performance. The test environment was comprised of 8 compute nodes with identical hardware. They were connected to an InfiniBand fabric composed of FDR and EDR switches in a fat tree topology with multiple routes. This chart depicted here defines the detailed hardware characteristics for the compute nodes. A new operating system image was built that supported BPF tools, benchmarking software, HPC scheduling, centralized storage, and the InfiniBand fabric. A provisioning server presented this image to the compute nodes. The chart here provides a description of the various software components. The high-performance LINPACK HPL benchmark is used as a reference to calculate the top-performing supercomputers in the world. The HPL benchmark is performing numerical linear algebra techniques to solve a series of polynomial equations. A series of HPL benchmarks were executed on a set of the compute nodes, with and without Berkeley packet filter probes, in order to measure the BPF probe's effect on performance. A total of 32 HPL benchmark tests were run using the 8 compute nodes. First, each individual compute node ran the benchmark. The nodes were then grouped into pairs to run the benchmark together. Next, they were grouped into 4s. And finally, all 8 nodes ran the benchmark as a single cluster, twofold. These tests were repeated using the BPF probes, and a script was executed to simulate low-profile attacks that the BPF probes were projected to detect. While the BPF engine is fast, it cannot compensate for BPF probes that are fired frequently or are inherently slow. Therefore, before writing a BPF probe, it is important to determine the questions that need to be answered. In this case, 4 BPF trace scripts were written. The first script logged DNS queries by tracing the relevant function calls in the GNU-C library. The second script detected processes changing from one user to another by tracing Linux PAM, the library responsible for handling authentication tasks. The third script detected when SSH was used to forward to TCP ports. And the final script traced TCP traffic with connections to external resources. These scripts were copied to each compute node and executed at the beginning of the benchmarks that measured BPF performance impact. Their logs were redirected to files on a shared storage system. For tests with BPF probes attached, a bash script was launched on participating nodes that simulated low-profile attacks. The script produced a timestamped log for each action. Every 1 to 15 seconds, it performed one of the following actions as an unprivileged user: triggered a DNS query of an external domain, escalated to a privileged user, opened an SSH tunnel, or attempted a TCP connection to a random private IP. The results of the benchmarks were analyzed both from a performance perspective and a detection perspective to show whether BPF tracing scripts can sufficiently detect attacks on compute nodes without degrading performance for researchers. The HPL results indicated that the BPF probes had less than 1% impact on compute node performance. In many cases, HPL benchmarks with BPF enabled recorded higher gigaflops than the non-BPF benchmarks. When paired by lows and highs, enabling BPF caused a performance loss of 0.21% in the low benchmarks and a gain of 0.05% in the high benchmarks. When paired chronologically, however, it caused a 1.62% loss in the first benchmark and a 1.46 gain in the second. For single node runs, Node 1 suffered a performance loss of 0.41%, the greatest loss of all tests. Node 8 was the only node with no performance loss, instead recording a gain of 0.02%. For 2-node runs, there were no instances of BPF causing performance loss. Node pairs 1, 2, and 7, 8 tied for the smallest gain of 0.12%, while node pair 3, 4 had the largest gain of 0.65%. The 8-node HPL results were unusual. These benchmarks were run twice so that there were 2 non-BPF results and 2 BPF results. Depending on how they were paired, the benchmarks either supported that BPF had low performance impact or painted a picture of unexplainable performance differences from run to run. Therefore, these results were deemed inconclusive and further benchmark testing is recommended. The logs of the 4 BPF trace scripts were cross-checked against logs from the low-profile attack script to determine whether the BPF probes were adequate in detecting unwanted behavior. Overall, the performance of the BPF trace scripts was exemplary, but the fidelity of the scripts was hampered by excess noise. Scripts often produced multiple logs for a single action of the attack script. They also produced logs that were triggered by the benchmark software itself. When DNS queries involved dig or host commands, the query was obfuscated. But all queries using wget, curl, and Python produced one accurate log per action. In conclusion, the BPF trace tool is recommended on HPC compute nodes for detecting malicious behavior. BPF trace scripts successfully recorded simulation attack activities without degrading performance beyond 1%. Future performance analyses could examine additional factors that cause variation in HPL results. BPF trace scripts should be improved as new features become available in future Linux distributions. While BPF trace scripts in this analysis were limited to only TCP, it would be valuable to write new tracing scripts for other protocols as well. Security practitioners familiar with kernel code can use their knowledge to produce new BPF trace scripts designed to detect attack scenarios occurring in the wild. If you're interested in more detailed information on this topic, please check out the companion report on the CSIAC website. On behalf of the CSIAC, we would like to thank you for viewing this podcast. We hope you found the content useful and informative. If you would like to provide us with feedback, please comment on this video or visit our website at www.csiac.org, where you can also find additional content to review. Thank you.
Did you know that CSIAC offers free monthly webinars featuring experts in the areas of cybersecurity, software engineering, modeling and simulation, and knowledge management? Come see leading industry professionals talk about industry practices and leading research. Make sure to visit www.csiac.org/webinars in order to subscribe to our mailing list and see when the next webinar series is available. There you can also watch previous webinar series to catch up. Visit www.csiac.org/webinars.